Welcome to Article Lab, the channel where we turn complex research papers in biomedical engineering, artificial intelligence, and electrical engineering into clear, engaging insights. Join us as we explore, critique, and break down cutting-edge studies in a way that's easy to follow and exciting to learn. Don't forget to subscribe and be part of our journey into the world of knowledge.
Welcome to the Deep Dive. We're the show that cuts through the noise, finds those fascinating nuggets in cutting-edge research, and, well, makes them make sense. Imagine if you could take just mountains of text, right? Especially critical stuff like in healthcare, and instantly pull out what matters, understand it. Sounds futuristic, maybe, but artificial intelligence is actually making this happen. It's giving us these incredibly powerful shortcuts to knowledge. Today we're digging into a really interesting research paper. It's called Biomedical Text-Based Detection of Colon, Lung, and Thyroid Cancer, a deep learning approach with novel dataset. This comes from Kubilay Muhammad Suneci at Osmaniye Korkut Adi University in Turkey. So our mission here is to explore how deep learning, this AI technique, can spot specific cancer types just from reading biomedical texts. We'll look at the study's unique methods, some surprising results, and what it could all mean for doctors making decisions down the line. Okay, let's unpack this a bit. We hear so much about AI in healthcare, right? Analyzing scans, predicting diseases. But this focus on text is fascinating. You know, the reports, the notes, the studies. Why is pulling knowledge from text, they call it biomedical text classification, or BTC? Why is that so important right now? What's the problem it's really solving?
Well, it's fascinating because AI is now tackling all kinds of data. And with these huge language models that have exploded recently, natural language processing, NLP, is just central. Think of NLP as the AI's ability to actually, read and understand like humans do. So BTC, biomedical text classification, it's fundamental for getting knowledge out of all this medical data. It's about taking unstructured text, like a doctor's notes or research findings, and turning into insights you can actually use. But it raises a big question for me. How do we get AI to go beyond just like scanning the words? How does it truly understand and classify information, especially for something as critical as cancer?
Right. So the goal here for this specific study was using deep learning to find mentions or descriptions related to colon, lung, and thyroid cancer in these texts. And the paper says this could really help clinicians. The potential for just rapid insights seems huge. For doctors, for researchers sorting through tons of papers.
Yeah. Okay, here's where I thought it got really interesting, really clever. A big goal was creating AI models that are generalizable, meaning they work on new data, not just the stuff they trained on. And to do that, they needed a new data set. But they didn't just grab one off the shelf, they actually made it, specifically for this. That really stood out. How did they even do that?
Yeah, that's a truly distinguishing factor. And honestly, kind of smart way around some common AI hurdles. They used ChatGPT, the free version actually, GPT-4 from OpenAI, to generate the text data. So first, they crafted about 50 unique questions about colon, lung, and thyroid cancer. Good structured questions like, what are early colon cancer symptoms? Or how can you prevent lung cancer? Or maybe what risk factors are linked to thyroid cancer, that kind of thing. Then, for every single question, they had ChatGPT generate 20 different answers. Diverse answers, semantically different, So the AI wouldn't just learn one way to talk about symptoms, for example.
Yeah.
And these texts were kept pretty short, like 40 to 100 words on average, concise.
That's already a neat way to build a data set. But then came the really smart part, the bit that made me go, aha. Technology. To stop the AI models from just memorizing keywords like spotting the word colon and saying colon cancer, which is called overfitting. Where the AI does great on training data, but fails on new stuff, they did something specific. They took out the words colon, lung, and thyroid from all the answers. Just replaced them with a space. Why was that such a big deal? It seems small, but why was it so powerful?
Oh, it's brilliant. Absolutely. Because, preventing overfitting is just critical if you want AI to work in the real world. Think of it like a student cramming for a test by memorizing exact answers. They might ace that practice test. But if the real test asks the same thing differently, they're stuck. They'd understand. By removing those specific cancer names, they forced the AI to learn from the context, from the surrounding words. It had to figure out what symptoms, what risk factors, what treatments are usually associated with this type of cancer without seeing the actual label. So the AI has to be genuinely smarter, basically. Learning patterns, not just keywords. This novel data set ended up having 3070 texts. Pretty balanced. 1020 for colon, 1020 for lung, 1030 for thyroid. Then they did the standard split, which is super important. 70% for training the AI, that was 2,149 samples. And the other 30% was kept aside for checking performance, 461 for validation during training, and 460 for the final unseen test. Yeah, this whole detailed process, especially removing the keywords, that's a really significant step towards building AI you can actually trust.
Okay, so they've got this really cleverly made data set. But like you said, computers don't read English. It's just dot text. What's the next step? How do you turn that into something the AI can actually crunch?
Right, that's the challenge. You need pre-processing. These steps are pretty standard in NLP, but absolutely vital. First, they tokenize the documents. So imagine breaking a sentence into individual words and punctuation. Each piece is a token. Then convert everything to lowercase, so cancer and cancer are seen as the same thing. And get rid of punctuation usually doesn't help classification much. Then came word encoding. They use something called doc2 sequence. It's like building a huge dictionary for all the words in their data set. Every unique word gets a number. So cell might become, 17, and tumor becomes 42. This turns the text into sequences of numbers. That's what the computer works with. And finally, to make training efficient, they cut or padded these number sequences to a standard length, 105 numbers or words long, keeps everything uniform for the AI model.
Got it. Numbers in, uniform length. So now the data is ready for the main event, the deep learning. And they didn't just bet on one horse, did they? You'd want to try a few approaches for something this important.
Exactly right. No, they tested 7 different deep learning architectures. You really want to see what works best for this specific problem in data. These included some big names in neural networks, LSTM, which is long short-term memory, also GRU, gated recurrent unit, and BiLSTM, that's bidirectional LSTM, plus some combinations. Just quickly, LSTMs and GRUs are really good at remembering patterns and sequences, like sentences. They have a sort of memory. BiLSTMs are even fancier. They read the text forwards and backwards, so they capture context from both sides. Often gives a richer understanding. All these models had some common parts, like a word embedding layer. That gives each word's number ID a richer meaning, kind of placing it in a meaning space near similar words. And of course, a classification layer at the end to make the final prediction: colon, lung, or thyroid. Importantly, they kept the training settings consistent across all 7 models, like using the atom optimizer, that's the algorithm guiding the learning, and an embedding dimension of 80, defining how rich those word meanings are. This ensures a fair fight between the models, but this raises a key question, doesn't it? How do you actually judge which model won? Especially in medicine, where getting it wrong can be serious. It can't just be about one simple score, surely.
That's a really good point. It's not just about getting an answer. Yeah, it's about getting the right answer reliably. What does right even mean when you're talking about cancer detection?
Precisely. And this study did a good job here emphasizing a whole set of evaluation metrics. That's crucial in healthcare. They didn't just look at accuracy, the percentage of correct guesses overall. Accuracy can be misleading. Like, imagine a test for a rare disease. A model that always says no disease might be 99% accurate, but totally useless.
Right. Yeah, I see that.
So they also calculated things like sensitivity or recall. That tells you how well the model finds the actual cancer cases. You want that high don't miss real cases. Then specificity. How well does it identify the non-cancer cases correctly, minimizing false alarms? Precision. When the model does predict cancer, how often is it actually right? You want confidence in its positive predictions. The F1 score. This balances precision and recall. It's a kind of combined score, useful when the cost of missing a case versus a false alarm isn't equal. And finally, MCC, the Matthews correlation coefficient. This one's considered maybe the most robust. It looks at everything: true positives, true negatives, false positives, false negatives, and gives a single score that's less easily fooled by unbalanced data. It's like the fairest overall grade. Using all these gives you a much clearer picture that the model isn't just lucky, but actually understands the task. Vital for clinical trust.
Okay, that breakdown of metrics is super helpful. It really shows the depth needed. So with all those tests and careful measurements, which model actually performed the best? Which one came out on top?
The winner was the LSTM Layers 1 architecture, so the long short-term memory network, a relatively simple single-layer version. On the validation set, the data used for tuning during training, it hit 91.32% accuracy, which is pretty solid, but importantly, it did well on those other metrics too. Sensitivity was 91.33%, specificity is strong, 95.67%, precision 91.49%, F1 score 91.32%, and that robust MCC score was 87.03%. And even on the final test set, completely new data, it held up well, achieving 85.87% accuracy, another plus. The paper mentioned this LSTM model was also quite fast and cost-effective to train. That's a big practical win for actually using it.
91%, 85% on the test set.
Yeah.
That sounds pretty good, especially given how they made the data set harder by removing keywords. But, you sometimes see papers boasting like 99% accuracy. So how does this 91% stack up? Is it genuinely competitive or is there a catch?
That's an excellent question. And this is where that novelty of their data set really matters, connecting back to what we discussed. The study itself points this out. Yes, some older research using publicly available data sets got super high accuracies, maybe up to 99%, but those public data sets might be smaller and less varied. One they mentioned only had about 996 texts total. Well, it's potentially an easier learning task for the AI. This study's data set, built from scratch with ChatGPT answers and specifically designed to make keyword cheating impossible by removing colon, lung, thyroid, it's inherently much harder. The AI had to learn deeper context, so hitting 91.32% accuracy on this tougher, arguably more realistic data set, that's actually considered highly successful and really promising for real-world use. It says good things about the model's actual understanding and the quality of their tough data set. It builds trust.
Okay, that context is crucial. So the results are strong because the test was hard. Makes sense. Now, this sounds great for researchers for advancing the science, but what about getting this AI power into the hands of, say, doctors or clinicians? Was there any step towards making it practical, a tool people could actually use?
Absolutely. And that's another really positive aspect of this work, focusing on application. They developed a user-friendly piece of software, a graphical user interface, or GUI. They called it Medical Text Prediction App. The whole point was to let people, potentially healthcare professionals who aren't AI experts, use the best model they developed easily and effectively.
Okay, so walk me through it. If I'm a doctor, maybe I get a complex patient report. How would I use this app? What does it look like?
Right. So imagine you, as the clinician, have this text, maybe a referral letter, a pathology report abstract, something dense. You'd open the medical text prediction app. It would have a simple text box. You'd copy and paste the relevant text right into that panel. There's a scroll bar so you can review it, make sure it's right. Then there's basically a button, something like predict the text label. You click that. Behind the scenes, it feeds the text to their best model, the LSTM one. And then in the classification panel, it shows the prediction: colon cancer related, lung cancer related, or thyroid cancer related. And they mentioned the prediction speed is fast, around 1 second. Now, obviously, this isn't making the final diagnosis, but can you imagine how helpful that could be? As a quick check, as a second opinion prompt, to help prioritize reading. It could really support the expert, potentially save time, reduce some of that cognitive load.
I was like, that's fast. Okay, so stepping back, looking at the whole picture, what's the big takeaway here? What does this study really mean for the future of analyzing medical texts? So wrapping up this deep dive, this study by Kubilay Mohammed Sunechi showed a successful way to use AI, specifically deep learning, to detect signs pointing towards colon, lung, or thyroid cancer just by reading biomedical texts. I think the real ingenuity was creating that brand new data set with ChatGPT 3070 texts and cleverly removing the main keywords to force deeper learning and prevent overfitting. That really stands out. The LSTM model came out as the winner, delivering strong, competitive results, especially impressive given how challenging they made the data set, and building that practical tool, the Medical Text Prediction app, shows a clear path from the lab to potentially helping out in clinics, saving time, and maybe even costs. It makes it feel more real.
Exactly. And I think this study really highlights how fast AI in medicine is evolving. It's not just about images anymore. Understanding language is becoming key. What's really exciting is where they see this going next. They talk about expanding it, more cancer types, handling much longer documents, maybe exploring even more advanced AI architectures. If you connect them to the bigger picture, you start to see a future where AI could be like this incredibly smart, tireless assistant for clinicians, sifting through endless text, flagging important connections, providing insights in seconds. This study feels like a solid step in that direction, showing AI can grasp medical context, not just words. So, here's a thought to leave you with. What if this kind of AI analysis wasn't just a standalone app, but built into every electronic health record system? Imagine doctors getting instant data-driven flags or summaries right there as they work, proactively guiding care. How could that change things? That's something powerful to think about as this technology keeps racing forward.
Thanks for watching Article Lab. If you enjoyed this video, make sure to subscribe and hit the notification bell so you don't miss our upcoming videos. We'll see you in the next one.